Hi everyone, I'm Xuan Wang from Beihang University. The title of our paper is TCIM, Triangle Counting Acceleration with Processing-In-MRAM Architecture. This is a joint work with University of Maryland and the Chinese Academy of Science. The graph or network has been critical to the information system, which has been widely involved in social networks such as Facebook, Twitter. For graph analysis, triangle counting gives the number of triangles in a graph. In social network, it indicates whether three people are friends to each other. There are also many other applications of TC. However, the size of such graph is huge, which can have 3 billion nodes. Existing TC approaches suffer from the bandwidth bottleneck, for it involves a large amount of data transfers. In-memory computing performs computation where the data resides, so it has appeared as a viable way to carry out the memory-intensive task like TC. And it can be even more promising with the emerging non-volatile STT-MRAM. However, developing in-memory TC accelerator is expensive for existing TC algorithm. Thus needs new TC method to enable efficient in-memory implementation. And this motivates our work in this paper. We propose to perform TC with massive bitwise logic operations. Let A be the adjacency matrix of undirected graph G. Then the value of Aij indicates whether there is an edge between vertices I and j. And A square Ij represents the number of distinct paths of length 2 between I and j. So in the case that there is an edge between vertices I and j, at the same time, I can also reach j through a path of length 2, where the intermediate vertex is k. Then vertices I, j, and k form a triangle. As a result, the number of triangles in G is equal to the number of non-zero elements in the interaction of A and A square. As we can see, TC can be completed by getting the end result of the rows and columns of the non-zero element, and then count the number of ones of the end result. Therefore, TC can be completed by massive bitwise operations. Here is an example. The graph has 4 vertices, 5 edges, and the adjacency matrix is given. First is the non-zero element A01. The corresponding row R0 and column C1 are executed with AND operation. Then the AND result is sent to the bit counter and get a result of 0. Similar for the other non-zero element, A02, A12, A13, and A23. Once the execution of the last non-zero element is finished, the accumulated bit count result is 2. Thus, the graph has 2 triangles. Here we only need 5 AND plus bit count operations to get the number of triangles of the graph. For the data flow management, the first row is used to process each row in the adjacency matrix, and the rest rows store the columns of non-zero element. And we can reuse the columns to reduce memory write. In case that the computational memory is full, we will adopt the least recently used policy, namely LRU policy, for replacement. To utilize the sparsity of the graph, we propose a data slicing strategy for graph data compression. For example, assume that row I and column J are to be computed. Then they will be partitioned into the same size slices. Only when the corresponding slices are both non-zero, for example, these two, slice 3, they will be loaded into the computational memory for calculation. Then the same way goes for slice 5. In this way, the memory requirement and unnecessary computations can be significantly reduced. Next is the overall sparsity-aware processing-in-MRAM architecture. The graph data will be first sliced and compressed. The non-zero slice pairs are loaded into the computational STT-MRAM array for bitwise computation. Its storage status is also recorded in the data buffer and utilized for data reuse and exchange. Then the peripheral circuit and the sense amplifiers are enhanced for in-memory TC computation. We conduct device-to-architecture co-simulations to validate the proposed TC accelerator. And we adopt 16 MB STT-MRAM as the computational memory. We can see that, on average, the non-zero slices in the 5 largest graphs only occupy 0.01%. Thus can significantly reduce the needed computations. And thanks to the cases of data heat, the data reuse scheme saves about 72% STT-MRAM memory write. As for data exchange, the largest graph needs only 16.8 MB without incurring any data exchange. As for the overall performance, we achieve about 50 times speedup against the baseline CPU implementation. And with PIM, another 25 times acceleration is obtained. Compared with the state-of-the-art GPU and FPGA method, the improvement is about 9 times and 23 times respectively. As for the energy savings, our approach has 20 times less energy consumption compared to the energy-efficient FPGA implementation. To conclude, we propose TCIM, a triangle counting in-memory accelerator with MRAM. Includes a novel TC method that uses massive bitwise operations to enable efficient in-memory implementations. We build a TC accelerator with a sparsity-aware processing-in-MRAM architecture, and it achieves encouraging speedups and energy savings. For the future perspective, we will work on research on universal in-memory graph computing accelerator to overcome the memory wall and power wall encountered by the von Neumann architecture. Thanks for your attending, and any questions?